Hello and welcome to For the Love of Wisdom, a YouTube channel on philosophy, free thought, and critical thinking. In this video we're going to be continuing the series on symbolic logic, and we're going to be looking at material equivalence and the rules of replacement. Material equivalence means that two statements have the same truth value, and this is our symbol for representing material equivalence. It looks like an equal sign, but it has an extra line in it. And it's roughly the same as equals. Here's what it means with a truth table. We have TTFF for P and TFTF for Q, and we see that where they have the same truth value, the whole expression is true, here at the bottom and here at the top. But where they don't have the same truth value, it's false, which are two combinations in the middle. And if we look over here, when we use the equals operator from various computer programming languages, we see that if we have two Boolean variables and set to true or false, it gives the same value as the material equivalence operator. It's true when they're both true or both false. It's false when they differ from each other. So it's true when they're the same, false when they're not. The main difference between equals and material equivalence is that material equivalence works only for truth values, and equals will work for numeric values as well. Okay, let's move on to our first rule of replacement. I should mention a rule of replacement is telling us that we have two different expressions that are materially equivalent to each other. And we're using the material equivalence symbol to show this, because it's saying this whole thing has the same truth value as this whole thing. And if you have one or the other, you can use a rule of replacement to infer the other one in a logical argument. So we're starting with material equivalence because it's about the very operator that we need to know to understand what the rules of replacement are. So this is telling us about the operator we're using in every rule of replacement. So it's saying P is materially equivalent to Q is material equivalent to the conjunction of if P then Q and if Q then P. It's saying if one of them is true, the other has to be true. That's what material equivalence is saying on this interpretation of it. Here we have another way of expressing material equivalence. It's saying either P and Q are both true or they're both false. So this is telling us what material equivalence means. Okay, let's move on to the next rule of replacement. Starting with this one, I'm going to start with the simpler ones, and I'm going to proceed on to the more complicated ones. So here's a very simple one, double negation, saying that P is materially equivalent to the double negation of P, or not P. In colloquial English, we sometimes use double negatives for emphasis. We sometimes use it for emphasis, but not in logic. So anyway, if you negate something, you switch its truth value. If you negate it again, you switch its truth value back. So a double negation is the same as the original. Okay, tautology. This is another very simple rule of replacement. It's saying that a statement is equivalent to the conjunction of it with itself, or is equivalent to the disjunction of it with itself. And this is very easy to see. P and P is going to be true whenever P is true, or false whenever P is false. And P or P is going to be true whenever P is true, or false whenever P is false. So they're material equivalent to P. Now we have commutation. This is about the placement of statements with respect to each other, their order, that is, how we order statements. It's saying that with disjunctions or with conjunctions, with or with and, we don't care about the order that they appear in. You can say P or Q is the same as Q or P. It doesn't matter. It's the same thing. It's just saying that one of them is true. And with conjunction, it's the same. It says P and Q is equivalent to Q and P. The order doesn't matter. Uh, all it's saying is that both of them are true. And I'll note here that the property of commutation also applies to addition and to multiplication in math. So if we have x plus y, that's equal to y plus x. And if we have x times y, that's equal to y times x. Okay, moving on to association. That's sort of similar to commutation. It also works for disjunctions and conjunctions. And what this is saying is that how we arrange them with parentheses makes no difference. So if we have P or, and then the disjunction of Q or R, that's equivalent to the disjunction of P or Q or R. And likewise, we can say P and the conjunction of Q and R is equivalent to the conjunction of P and Q and R. As long as we keep our symbol the same, and our symbol is, rather I should say, as long as we keep the operation the same and the operation is completely symmetrical, that is, commutation applies to it, then association can also apply to it, and that works for the or and the and. We can arrange them any way we want to. And with association and commutation together, we can arrange them in any order and place the parentheses however we wish, and it doesn't affect the truth value of the expression. Likewise, in mathematics, you can arrange if you're adding numbers together, you can arrange the numbers together in any order and with parentheses in any way you like, and the sum is going to be the same. So here the sum of x plus the sum of y plus z is equal to the sum of x plus y plus z. And likewise for multiplying, if you can say x times the product of y times z is equal to the product of x times y times z. And you may notice subtraction and division do not work like this because they are asymmetrical. Also, conditionals are asymmetrical, and so association does not apply to them. Okay, now we're going to get a little more complicated. With distribution, we're using both the and sign and the or sign in a single expression. Here we have P and the disjunction Q or R. That's equivalent to the disjunction of the conjunction of P and Q and the conjunction of P and R. So P and the disjunction Q or R is equivalent to the conjunction P and Q or the conjunction P and R. And here's an example. Pat went to the dance and danced with either Quentin or Rachel. That means the same as Pat went to the dance and danced with Quentin, or Pat went to the dance and danced with Rachel. Here's another version of distribution. This is just the same as this, except we have switched the ors and ands around. So this says P or the conjunction Q and R is equivalent to P or Q and P or R. An example is, I have been to Paris, or I have been to Queens and Rome. That means the same as I have been to Paris or Queens, and I have been to Paris or Rome. Moving on, we get to De Morgan's theorems. De Morgan's theorems are telling us alternate ways of expressing the negation of a conjunction or of a disjunction. Okay, first of all, when we negate a conjunction, what we do is we create a disjunction and we negate each disjunct. So the important thing here is that when we switch from one side to the other with De Morgan's theorems, we change the sign, not the sign, we change the operator either from and to or from or to and we move the negation. If the negation was of the whole thing, then it's now of each individual part. And if it was already of each individual part, then we change it to the negation of the whole thing. So that's how to do De Morgan's. And the first kind is the negation of the conjunction. So we negate P and Q. That's equivalent to not P or not Q. And here's an example. Peter and Quentin are not both married. That means the same as Peter is not married or Quentin is not married. And here we have the denial of a disjunction. And that's equivalent to the conjunction of the denial of both parts. And we have a way of saying this in English. We say neither nor. So we would say neither P nor Q is equivalent to not P and not Q. Here's an example. Neither Peter nor Quentin are married. That means the same as Peter is not married and Quentin is not married. Since I often make use of De Morgan's when I'm computer programming, I'll also show it to you in computer code. The language I'm specifically using here is PHP. Other languages may use code very similar to this. I'm following PHP's convention of putting a $sign before a variable name. Okay, so here the exclamation mark is our not operator. The double equals is our equals operator. The double ampersand is and. The double vertical bars is or. And so what you can write like this, you can also write like this. And what you can write like this, you can also write like this. So this is the negation of P and Q. That's the same as the negation of P or the negation of Q. And here we have the negation of P or Q, which is the same as the negation of P and the negation of Q. Now we have material implication. This is about the conditional. You may remember from a previous video on conditionals that the conditional is about material implication. It's not about cause and effect. It's just about the relation between truth values. And this is saying that the relation between truth values of P and Q and the expression if P then Q is the same as the relation of truth values between, in this expression, not P or Q. Here's an example of this. If you advance your pawn, you will get a queen. That means the same as you will not advance your pawn or you will get a queen. Let me show you what implications this has for computer programming. There are two different ways we can do the same thing in computer programming. Here is the usual way. We say if P, then do Q. So P is a function here and Q is another function. It's saying if the P function returns true, then go ahead and do the Q function. Well, there's another way to get the program to do the same thing, assuming that our logical operators have the feature of breaking away, so that in this example, if this whole expression on the left side of the or happens to be true, then it automatically knows that the whole expression is going to be true and it stops evaluating it. So if P turns out to be false and not P will be true, and it will stop and it will not evaluate Q. But if P happens to be true, then not P would be false, and then it will go ahead and evaluate Q. So just like up here, it would be evaluating Q only if P happens to be true. So these are alternate ways of doing the same thing. And if you want to write obfuscated code, this is one way to do things. Okay, let me also show you this one with a truth table because it can be a little more counterintuitive. Because we sometimes think of if-then not in terms of material equivalence, but in a richer sense. And we have to remember that in symbolic logic, this horseshoe is just material implication. It's not any other relation between the two statements in it. Okay, to make our truth table, we first write down all the combinations of truth values for our variables, for our statements here. And since we have two statements, we have four combinations. So we go with TT for P, then FF, and for Q, we just alternate between T and F. We're going to do it here, and we do it also over here. And you may remember that if P then Q is true in every instance except when P is true and Q is false. It's saying this can't be. In the case where P is true and Q is false, if P then Q is false. But otherwise it can be true. Okay, over here, we negate the value of P, so we get FFTT. And then it's a simple matter of comparing this column with this column to find out what the whole truth value is. So false or true, false or true, that's true. Here, false or false, that's false. Here, true or true, that's true. And here, true or false, that's also true. So you can see it has the same truth value for every combination as if P then Q has. So here's where it's false, and here's where it's false. Otherwise, it's true. Okay, let's move on to transposition. Transposition is telling us that if we have the conditional if P then Q, that's the same as having if not Q, then not P. And let's recall how modus tollens works to understand this one. The rule of modus tollens says that if we have if P then Q and we have not Q, we can conclude from that not P. Well, that's enough to tell us that this follows from this. So if we have not Q and we can get not P, that means we have if not Q, then not P. So in transposition, you basically reverse the positions of your statements and negate both of them. Now we have exportation. Exportation says that if we have P and Q, if P and Q, then R, that's equivalent to if P, then if Q, then if R. And let me show you the implication this has for computer programming. These are basically equivalent to each other. We have to remember here that with our logical operators are supposed to be designed to break away if they know the truth value immediately. So, and here for example, if P and Q run code, so if P is true, then to know the whole truth value, it also has to evaluate Q. And then it can run the code. Okay. And that's equivalent to saying if P, then if Q, run code. This is going to run the code only if P and Q are both true. And likewise, this is going to run it only if they are both true. So these are functionally equivalent to each other. They're going to end up doing the same thing. Well, that's it for the rules of replacement. Thank you for watching. Take a look at my previous videos on symbolic logic if you haven't, and stay tuned for future videos on symbolic logic.